Okay, good morning. So let us start today's lesson. So this example, which is on display, hopefully we could do it in a reasonable way, and hopefully you realize that this set, even though it's bounded above, has no supremum in Q. So this motivates us to impose a new axiom that is only for the system of real numbers, and it is called the completeness axiom. The way that we are presenting the course here, we call it axiom, but if you see it in the book, it is called a theorem. The reason is that in mathematics, everything is a set. So essentially, if you want to do everything properly in mathematics, you only accept some axioms about sets in set theory. And then you start constructing even numbers out of those axioms. So when you start in mathematics, you start from set theory, you don't have anything in your hand except the notion of a set, which is a primitive notion and it is not even defined. But we impose some axioms on sets, and then using those axioms, more or less out of nothing, we start constructing the whole mathematics. So even 0, 1, 2, these are sets in set theory. And we set up this, if we have time, we will go through some part of it under the, so you first have sets, and then you construct natural numbers, and then using some tools, you construct integers, and then you construct rational numbers, and then you construct real numbers. So if the book has mentioned this as a theorem, it means that if you do it in a proper way, then it will be a theorem that guarantees you the set we construct as real numbers has this property. And it is also shown that that set up to an isomorphism is unique. So if you can come up with another set with all those properties of the set of real numbers, it is either exactly identical to R or it's a carbon copy of R. So, but because I haven't talked about those things here, so many more elementary books call it an axiom. So we want to impose this axiom on the set of real numbers. So far you can imagine that the system of real numbers is what you have learned before. You can add them, multiply them, all the properties you really know about set of real numbers. But now we want to add one more axiom on top of that, which is called the completeness axiom. And the previous example was trying to motivate why we need this. So there are some holes in the set of real numbers because the set of irrationals and the set of real numbers have everything in common, except that the set of real numbers have some holes in it. We want to fill up those gaps. And then to do that, we need this axiom. So for the time being, you can consider this as an axiom, but if we have time, we'll probably go and try to talk at least a little bit about what does it mean to construct numbers from sets. So this is the axiom, completeness axiom. What does it tell us? It tells you that, let me write it in a simple way. So the completeness axiom axiom is a statement we accept its truth, and then we explore its consequences. Yes. So the one that I have written in a math form is something it's good to remember. So if you have a set which you know is a subset of the real numbers, and it is granted that it is not the empty set, and you also know that A is bounded above, then from these two, you can conclude that it is guaranteed that this A has a supremum within the set R. So you don't need to extend R, okay? So supremum of A exists in R. So this is an axiom we accept here, and then we try to explore its consequences. Any questions? So if you want to prove the existence of supremum, remember, you have to show that your set if you want to prove that the supremum of your set, which is a subset of R, exists, you need to show that it is not empty, and you need to show it is bounded above. This axiom grants that the supremum exists in R. That's the content of the axiom. Okay. But immediately I have given you this example. So it takes a long time. I did it at home very fast. It took 7 minutes. 7 minutes is too much for this lesson because that's not a very important part of today's lesson. But I want to sketch the solution for you. So what the problem tells you is a state. This one, by the way, I called it the axiom, completeness axiom. Sometimes it is called the least upper bound property. Yes. So if you go to the previous one, the least upper bound property is another name for the same axiom. So now I am using this. I want to rely on your intuition a little bit. So state the greatest lower bound property of R and prove it. In the previous case, I didn't ask you to prove it. I accepted it as an axiom. But now this will be a consequence of this axiom that we accepted, hopefully. And now we can call this a theorem. But in your book, both of them are called theorems because of the explanation I mentioned to you. Okay? So can you explain this? So this is example 2.3. And because I am just numbering them consecutively, so if you don't mind, just let me write the number. So 2.3, so how can I state that? So let me start with this one. So I would say that if my set B is not empty and is a subset of R, can you change this accordingly? Based on your intuition, what do you think I will write here? B is bounded below. Then what do you think we can conclude from here? Yes? Infimum of A exists in R. Infimum of B, thank you. Existing. So a sketch of a solution. So the point is that, let me give you a picture. For example, let us say that this is the set of real numbers. I don't want to prove it, but it's a very good exercise. I really want you to go home and sit down and think about it so that you can write it properly. It's a very simple exercise. Let us imagine here is 0, and let us imagine that this is my bounded below set. Yes, so let me call this B. So for the argument, it doesn't matter if the whole part of it is on the positive part, the whole part of it is on the negative part, or some part is on the negative part, some part on the positive. So you see, this is a set. Of course, the way that I did it is not bounded above, but what is important, it is bounded below. But I want to mention, this is we want to show that if I have a non-empty subset of R which is bounded below, then the infimum exists. So if I ask you to point it, you will tell this number is the infimum. As simple as that. Okay, but we want to prove it rigorously. If you want to prove it rigorously, I want to define a set which is bounded above. So what I will do, I will mirror image this set with respect to this O, and then something like this will happen. Yes, so here, and then it goes down. Yes. So this set, we call it A, okay? But A is, we sometimes call negative of B. So A is the set of all numbers minus B's, so that B belongs to A. B belongs to A. So what you say, you would say let A be this set. What I am doing geometrically is this one. Then you can see that. Do you see that this A is not empty? So you see this is my set, original set. I myself, I am constructing a new set in this way. I am saying that whatever number you see in B, multiplied by a negative sign and put it in a new set. Then you construct a new set. Okay? So this set is not empty. Do you agree? Why? Because B was not empty. If what was not empty, I multiply it by a minus sign, I get something here, okay? And then what you need to see is that based on this geometric picture, you see that A is not empty, but you have to rigorously prove all these parts. Write it down, it's a good exercise. And you also see that A is what? Bounded above. Do you agree? At least this is something, of course, you have to prove rigorously, but it is very clear in this picture that A becomes bounded above. So A is not empty and it is bounded above. I can use completeness axiom to grant the existence of the supremum of A. Yes, so this will be the supremum of A. Yes, this is granted by the axiom. And now we want to prove the existence of this one, but you can guess what it should be. It should be minus supremum of A. Yes? And then you say that, okay, because this set is bounded above, you have to prove it. The existence of supremum of A is granted. And then I claim minus this number is the infimum of my original set. You write it down and then prove it. So you claim something. A supremum of A minus supremum of A is equal to infimum of B. And then you prove this claim. It's an extremely simple exercise, but I really want you to sit down and really write the proof. It's very simple. It's a very good exercise. Any questions? Is that idea clear? So I want to prove that this has an infimum. The creativity part is to construct a new set in this way. This set becomes bounded above. The existence of sup for this one is granted. Then you claim out of this picture, it is not very hard to guess, that the minus of this number will be the infimum of my set. This is your claim, and then you prove it rigorously. Okay? How should you prove that something is an infimum? You should first show that this is a lower bound, and you should show that it is the smallest, the greatest lower bound. 2 steps. Yes? Okay. So now this is a very important theorem, a very simple one, Archimedean property. It tells us that if x and y are real numbers and if x is positive, then there is a natural number little n, so that when you multiply it by x, it becomes greater than y. Okay? So theorem 2.4, what we have, we know that x is positive and y. So let me write it in this way. X and y are positive, are real numbers, but x is positive. I want to grant the existence of a natural number so that when I multiply it by the positive one, it becomes greater than y. Okay? Intuitively, is it clear for you? So if I give you a positive number and I give you any other number, it is very clear by adding that number appropriate number of times, you can pass any threshold. Yes? If I have a very long stick and I have a, I don't know, matchstick, then I can, by repeating that matchstick appropriate number of times, the length becomes longer than any length. That's the meaning. It's very extremely simple. But I want to prove it because I want you to see, to get familiar how we use these theorems. So this, I want to prove it rigorously by proof by contradiction. So, to the contrary, well, let me write it like this. Let us assume that this is not the case. But I want you to tell me what is the meaning. Let us assume this is not the case. Then, okay, can you tell me? I want to prove that there is a number, a natural number, so that this happens. If you agree with me, fight is over. If you disagree, then what you should have agreed to. Can you tell me? There exists an n in n for which n times x is greater than y. What is the negation of this statement? Yes?
For every n in n, nx is less than y.
Less than or equal.
Yeah, yeah.
Yes, exactly. So then it means that for every n in n, nx is not greater than y, which means less than or equal to y. Is that right? If that's not the case. And now we define a set. These are the techniques that you have to learn. So let A be equal the set of all nx's such that n belongs to n. Okay? Now, do you agree that A is not empty? Do you agree that? Do you agree with that? Yes, because x is given, n is an arbitrary natural number, you just multiply it here and put it here. So you have actually infinitely many of them there. So it is also a subset of R. That's also understandable. Because x is a real number, n is a natural number. When you multiply, then definitely it becomes a real number. But is it bounded above? Is it bounded above? Yes, yes. Don't say no. Because we are fighting, yes? You told me you didn't agree with what I said, so you have to agree with this one. So it means for every n, nx cannot go beyond a threshold. Nx are elements of my set. They are not going beyond y. Is that right? So A is bounded above by y. Yes? So now completeness axiom grants a supremum of A exists. Yes? Understandable? Okay. So we say that let A be the name of the supremum. It's usually better to give it a name. You can work with the notation as well. Is that understandable? Okay, but now A is the supremum of A. Okay. Now, what I can write, I can say that A minus X is less than A. Do you agree with this one? Why? This is why it is important. You see, they haven't mentioned anything about Y, but they have mentioned that X is positive. Okay, and this needs X is positive, yes? So since X is positive. Okay. So now let me write something here. A minus X is less than A. A is supremum of A. You remember, I told you remember it. I wrote it here, it was wrong. One of you actually corrected me. That one I wanted to remember. So if I have a number which is smaller than the supremum of a set, what can I immediately conclude? I can conclude the existence of an alpha in A such that A minus X is less than alpha. Do you agree? This is the picture I told you. It's extremely important. So let me write it again here. So let me write two things here. Okay. So if A is supremum of a set, and then you know that alpha is smaller than A, what can I grant? I can grant the existence. So let me write this a different name. So if I know B is less than A, then I can grant the existence of an alpha in this set such that alpha is less than B is less than alpha less than or equal to A. This is very important. And then I told you the picture. Yes, the picture was simple. So if you have this one, the set A, and here is the supremum. If I choose a number smaller than my supremum, definitely there is a number which is greater than the number I have chosen. Yes, that's something that you know. Okay, so you also need to be able to fill this up. If A is infimum of A, and this time B is greater than A, then again I can grant, sorry for the mess, I can grant the existence of an alpha in A, but this time what happens? B is greater than that one, so it means that B is greater than alpha is greater than or equal to A. Yes? Is that understandable? So if for this one, if this is infimum, and you give me something greater than the infimum here, then I can have an element which is greater than or equal to A, and it is still less than B. That's this. So whenever you forget, try to visualize this and then get it. So that's what I'm using. If I have a number smaller than a number, this number is the supremum, this is granted. Is that clear or not? Yes, everyone? Because that's very important. I want you to really understand that. It's very simple, but very important. I will use it a lot. If a number is smaller than the supremum, I can find an element within the set which is greater than that given number. Okay, but now, what is the form of alpha? Can you tell me what alpha looks like? Because alpha is in this set, and everything in this set is a multiple of n. Is a multiple of x, is a natural multiple of x. So when you say that alpha belongs to A, so this means that there exists an m in natural numbers so that alpha is equal to mx. Is that understandable? And then I put it here. So A minus x is less than alpha, and I know that alpha is equal to mx. So this means that A minus x is less than mx. Okay? And then I move x to the other side and factor it out, and that is your contradiction that you need to tell me why that's a contradiction. Just let everyone think about that. If you have any questions, please let me know. But I want you to tell me why this is now a contradiction. Yes?
Because m plus 1 is also a natural number, so that means it's in the set. m plus 1x is in the set.
In the set.
But A is supposed to be the supremum, so it's
That's
you found a bigger one.
Exactly. So hopefully you agree that this belongs to A again. Because I told you every natural multiple of x is in A. Yes? M is a natural number, so n plus 1 is a natural number, so it's a natural number multiple of x. Where does this live? It lives in the set A. So this is in A. But what was A? A was the smallest upper bound. So it means the upper bound is smaller than one element within the set, which is the contradiction. Is that clear? So this means that this cannot happen. So these are the techniques that you need to learn in analysis. So especially defining a new set in a little bit creative way to understand this. So is the proof understandable? Okay. So this is called the Archimedean property, and we usually use this version of it, which is very important, especially when we go to limits and things like that. So why this is true? This version, remark 2.5, is actually telling me that if you have a positive number of epsilon, no matter how small this is, then you can find a natural number so that for every n in n, if n is greater than or equal to 0, then there exists a natural number n naught in n, so that for every n in n, so that n is greater than n naught, 1 over n is less than epsilon. Okay. Okay. By the way, this is very simple. Let me make it very clear. So you see what does it mean? Epsilon is a positive number. So let us exaggerate. Let us assume that epsilon is here. What does it tell you? It tells you that you can find a natural number so that 1 over that natural number is smaller than epsilon. Yes. So even if I give you epsilon 1 over 1000, you can choose 1 over 10,000. Becomes smaller than. So this is extremely simple. But I want you to understand this is a consequence of Archimedean property. So why is that? So you see, if epsilon is positive, do you agree by Archimedean property? How should I write it for simplicity? So Archimedean property, there exists a natural number such that n naught times epsilon is greater than 1. Do you agree? So this is the case. If you give me a positive number and another number, any number that you like, in which case I have chosen 1 for y, and I'm writing this relation. So there exists a natural number so that when I multiply it by my epsilon, it becomes greater than 1. So that's an Archimedean property in which I have chosen 1 for y. Okay, I can choose it for anyone. And then what does it mean? This exactly means if I divide everything by n naught, this means that epsilon is greater than 1 over n naught. Or 1 over n naught is less than epsilon. Yes? Okay, but if I choose n greater than n naught, that's even better. Yes, because if n is greater than or equal to n naught, what I can conclude that 1 over n naught is even less than 1 over n. 1 over n is less than 1 over n naught. Yes? And then this is smaller than epsilon. Yes? But you can use it, for example. So if you want to just say that there is an epsilon, you just say Archimedean property. This is correct. Okay, you don't need to prove anything. But is that clear? Yes. Okay. So now let us go to another theorem, which is also a simple fact. You already know about that. But it is good to know. Density of rational numbers. If you give me two real numbers, one of them is smaller than the other one, definitely there is at least one rational number between any two distinct real numbers. Yes? It's a very simple idea, but if you want to do them rigorously, you have to do them in this way. So now 2.6. So the density of rational numbers. So x and y are in R, and I know that x is less than y. I want to prove that there is an R in the set of rational numbers so that x is less than R less than y. So between any two real numbers, there is a rational number. Okay? So how should we do that? So you are telling me that x is less than y. Okay, so I can grant that y minus x is positive. Do you agree? And then what I can conclude by Archimedean property that existence of an n in n is granted such that when I multiply it by y minus x, it becomes greater than 1. So can you feel that? So if you compare it with the Archimedean property, n is the same here, but y minus x is playing the role of x, which I can give the role because it is positive, and 1 here is playing the role of this 1. So that's why when I write Archimedean property, I am correct. Okay, but then what does it mean? It means that ny minus nx is greater than 1, so this means that nx plus 1 is less than ny. Do you agree? So I was able to show the existence of an n for this case. So I was granted by Archimedean property that a natural number with this property exists. Okay, but here I will be a little bit sloppy because properly, if I want to tell you properly everything, I have to grant you the existence of the floor function. But let us accept that part. Okay, so what I want to do, I want to say that, do you agree with what I am writing here? This one is less than the floor of this number plus 1. Yes, do you remember what the floor is? So if you have any number here, A, so let me write it, I don't know, alpha. If I say what is the floor of alpha, what does it mean? If alpha is an integer, floor of alpha is the same number as alpha. But if it is not an integer, you always go to the left and pick the first integer. That is the floor. Is that right? For example, the floor of 2 is 2. The floor of minus 2.1 is what? Minus 3, because I go to the left and I pick the first element, first integer. So it is minus 3. Yes? But hopefully you agree that any number is smaller, strictly smaller than its floor plus one complete unit. Yes? And then the floor of every number is less than or equal to the number. Because we always either stay still if it is integer or we go to the left. So this means that this one is less than or this equal to this one, and then I add 1. Yes? And now we know that nx plus 1 is less than ny. Yes? So the bottom line, I don't like it, I drop it, and I will conclude this, that nx is less than this number, is strictly less than this number. Do you agree with what I have written now? Okay, finish the proof, please. What was the goal? My goal was to grant the existence of at least a rational number between x and y. So what should I do? What? Yes?
Divide by n.
Divide by n, yes. Divide by n. So this becomes x. That becomes the floor of nx plus 1 divided by n. This becomes y. Is the theorem finished? Is the proof finished?
Yes.
Yes, because this is definitely a rational number. What is a rational number? It's a fraction whose numerator and denominator are integers. Yes? The denominator is a natural number, so automatically is an integer. But the floor is always an integer. If you add 1 unit to it, it's also an integer. So integer over an integer is a rational number. It's a rational number. And the proof is finished. So you see that everything fits in place. It's very beautiful, you know. But of course, how many rational numbers do you expect? How many rational numbers do you expect between two real numbers? Definitely many. Why? Because there is one. Yes. Okay. And then between these two, you can find another one. And between those two, you can find another one. So there are infinitely many. But what is your guess? This is one exercise that I have asked you to do. What is your guess about rational numbers? Irrational numbers. Can I say between any two real number there is also an irrational number? Intuitively?
No.
Between any two real numbers, is there any irrational number?
Probably.
Yes. The answer to this is also yes, but you have to be a little bit more creative. So this is one of the exercises you should do. So remember, that's also true as well. Yes? Understandable? Okay, so now let us go to the next one. So this is also good. So the theorem says that the rational numbers are everywhere. So no matter how closely two real numbers sit, there is always a rational number between them. Okay, so that's something intuitively. Okay, so the next thing, of course, we will talk about sequences extensively later, but I need a little bit of definition of a sequence here. So what you have learned before in high school, sequence is a list of ordered numbers, and repetition is also allowed. So when I say that I have a sequence, so this is definition 2.8. So if I say that I have a sequence, I can write, 2, 5 minus the square root of 2, 5 again, 2 again, and I square root of 3 over 2, and etc. So if I have a list of numbers, but infinitely many of them, that is called a sequence in mathematics. And then you see that what matters for us is that order matters. If I just take these two and interchange them, then keep everything intact, I have a new sequence. By definition, it is not the old sequence. And then repetition is allowed, so it is not like a set. Yes? For example, you have seen something like this. minus 1 to the power of n is a sequence, because usually these sequences are useless in mathematics if they are not ordered. I mean, if there is no pattern among them, there is nothing that much we can study about them. So we usually in mathematics deal with only sequences with some kind of nice pattern so that we can study them. Okay, so for example here, if I ask you what is this sequence consists of infinitely many terms. This is definition of a sequence, but all the terms are either 1 or minus 1. So I have minus 1 for the first one, because if I choose n equals to 1, I get minus 1, the second one is 1, minus 1, and 1, and etc. But if I want to ask you what are the only elements involved, there are only 1 and minus 1. So I can write it in this form. Okay, but this is not the sequence itself. Okay, because in more advanced mathematics that we want to deal, sequences are not, this is a very good intuitive way to think about sequence, but sequence is a function. In mathematics, when I say a sequence, it means a function, but its domain is n. And its codomain is a set you like. Okay? When I say that I have a sequence, it means that I have a function from the set of natural numbers to any set. Okay, then I would say that f is a sequence in A. But if this A is famous, for example, if A is the set of real numbers, instead of saying that f is a sequence in R, I say f is a real sequence. If this one is the set of complex numbers, instead of saying that f is a sequence in C, I would say that f is a complex sequence. Otherwise, I say that this is a sequence in A. So it means the outputs are in A. And of course, usually, instead of, you know that when I have a function f acting on this, it gives me the nth term of my sequence. So this is the nth term, but usually in this sequence notation, you don't write it in that way, you write it as a sub n. Okay? So that's the definition of a sequence that I have written here. I don't know, this is a very common notation, I don't like it, you know. They denote this sequence by this notation. It's a bad notation, do you agree? In more, I don't know, the book is also using, your book is also using this one, but the best way is to denote it like this. Either you can write n from 1 to infinity, or I would prefer to put a pair of brackets rather than curly brackets. Because when you use curly brackets, it reminds you of a set, and in a set order doesn't matter, but in a sequence it matters. So be careful about this point. So from now on, I will use this notation if I want to be, but this is the notation in your book as well. Is that clear? Okay, so now let us go to the, okay, I have already talked about this. Let me read it for you. So a sequence is not just a set of numbers, it is an ordered list, and repetition is allowed. For example, that sequence you see is a sequence, but the set of its values is only minus 1. Okay, so we can talk about a set, but the set of values. Okay, now this is probably the most important definition today, which I'm sure that you're already familiar with, and we also learned a little bit about this in abstract algebra. So two sets A and B are called equivalent or equinumerous. Yes, written like this if there exists a one-to-one function from A to B, from A on to B. Is that clear? A bijection. So I say that two sets are equivalent. So this is definition 210. If I have two sets, I say they are equivalent. And by the way, this is not a coincidence that we are using the same tilde in abstract algebra. Do you remember this tilde was used for an equivalence relation? And this is also an equivalence relation because every set is equivalent to itself. So let me write it. So this means that there exists a function. This means that there exists a function from, for example, A to B, 1 to 1, and on to. Okay? So do you agree if this happens, somehow we can say the number of elements in A and the number of elements in B are the same? Okay? But if the sets are infinite, we cannot count them and say that they have the same number of elements. Yes? So if we can establish a one-to-one correspondence between them, then we have to accept that the number of elements within each one of them should be the same. Yes? For example, if there are a lot of students outside and then we have a big classroom here with a lot of separated chairs, so if I ask the students go to the classroom and take one seat, and then after the turmoil is actually settled down, when I look at the classroom and I see there is no empty places and there is no student without any seat, even if I don't know the number of seats in the classroom and I don't know the number of students outside the classroom, after this is settled, I can know the numbers are the same. Still, I don't know what is the number in each one of them, but I can understand the number are the same. The number of chairs and the number of students are the same. Okay? So the same idea you have to admit, because it is a little bit counterintuitive in the beginning, but don't resist. If this is so natural to you, the other case for the infinite case should also be natural to you. Okay? So, now, do you think that this is a good notation? Is it an equivalence class? Is it equivalence relation? Do you agree that every set is equivalent to itself? Yes, so what is the bijection there? Because when you want to prove two sets are equivalent, you have to grant the existence of at least one one-to-one correspondence. Yes?
The identity.
The identity. And then do you agree it is also symmetric? If A is equivalent to B, do you agree B is also equivalent to A? So if A is equivalent to B, the existence of F is granted, but because it is bijective, it is also invertible, and the inverse is also bijective. This is simple to prove. And so it means that B is also equivalent to A. And if A is equivalent to B and B is equivalent to C, can I grant that A is equivalent to C? What is the technique there? The composition of functions. Yes? This is not a coincidence, so that's an equivalence relation among the sets. Okay, so now this next example, and of course this is an extremely simple example, show that the set of natural numbers is equivalent to the set of non-negative integers. Okay, so example 2.11. So what do I have? I have natural numbers 1, 2, 3, 4, etc. And I have the set of non-negative natural numbers. Non-negative natural numbers start from 0, 1, 2, 3, etc. So the claim is that the number of elements here and there are the same. Of course, we cannot count them because both of them are infinity, but we can say the cardinalities are the same. It means that the infinities are of the same size, because we have different hierarchies of infinities, which was very confusing for mathematicians in the beginning of the 19th, and the end of the 19th century, beginning of 20th century. Okay, so it's also a little bit crazy idea that you say that at the end we have to admit that these numbers are, the number of elements within these two sets are the same. Okay, why is that? First of all, do you agree this is your one-to-one correspondence? So we are just establishing the one-to-one correspondence, and this will never end. Okay, but if you want to do it a little bit more rigorously, you should introduce your function. So if you don't mind, let me call it n, and let me call this one, what should I call? Let me call it b. Okay, so then I'm claiming that n is equivalent to b. So this is already a good picture. Sometimes we rely on this intuition in this course. You want to sketch the proof, but sometimes we have to be more precise. To be more precise, it means that you have to offer me the function. Yes, so what is the function? Yes, you want to answer?
Minus 1.
What? F of x equals to?
X minus 1.
X minus 1. So, do you agree that this will take me from n to b? Yes, because x is minimally 1, so x minus 1 is minimally 0, so it's correct. For example, can I define it like that? No, because if I choose x equals to 1, it gives me 2. So what is the problem with this function?
It's the inverse.
Now, what is the problem with this function? Is it, of course, I want to take it from N to B.
It's not onto.
It's not onto. Yeah, so there is nothing wrong with it because it really respects, it is taking elements from N and give me elements from B. So that part is okay. It is also one to one. It's injective, but it's not surjective. It's not a good function. But this one is a good one. And it is very simple to prove that this is one to one and injective and surjective. So this is your, based on this, you have to admit the number of elements within these two sets are the same. So we say cardinalities are the same. And usually cardinalities are denoted by this. For example, I say cardinality of this N is equal to the cardinality of this B. Any questions? Okay. So now this is something you need to know, and there are different conventions here. I want you to know these definitions by heart. So we want to define what is a finite set, what is a countable set, and what is an uncountable set. Okay, so let me explain it here on the board. You can see the slides. And I am using the convention in your book. But there are slightly different conventions. So here, this is the 2.12. Okay, so we have these terms: finite, countable, and uncountable. Okay, so number one, finite. When I say a set is finite, so let me call my set A. A is said to be finite if A is either empty or there exists a natural number such that A is equivalent to this set. So it means that you can establish a one-to-one correspondence between your set and this set. In that case, you say that my set is finite. Is that right? So the second case is the case that it is countable. Okay? Is this the same order I have written? Yes. So A is countable. What does A countable means? Only this one. So in some books this is different. I am following the convention in your book. So the word countable automatically means infinitely many. Okay? So, and that means that when I say my set is countable, it means that I can put it in one-to-one correspondence with the whole set of natural numbers, not just part of it. So when I say countable in this course, I always mean it is infinitely, there are infinitely many elements. And there is another statement, so let me just write it here: at most countable. It means what? It means either one or two. Okay? Either one or two. Okay? And finally, if none of the cases, if we have a set which has none of these cases, then we call it uncountable. So 4, uncountable if A is not at most countable. How should I type it here? Yes, it is not at most countable. That's correct. Because countable means either one or two. When you say neither one nor two, it means uncountable. Is that right? So this means that these two are called, these are infinite sets. So when I say that I have an infinite set, my set could be countable or uncountable. There are two different infinite sets. Yes, please.
But what about the empty set? It's not finite. Does that mean that
it is finite?
Well,
by definition, empty is finite. Finite means either this or this.
Oh, okay, yeah,
Yes.
sorry.
Yes.
Sorry.
Okay. And then these two together means at most countable. Yes? In some books, when they say countable, they mean finite or countable. I'm not using that notation. So whenever I say that I have a countable set in my notes as well, it means this is there is a one-to-one correspondence between my set and the set of natural numbers. So automatically it means it is infinite. Is that right? These are just definitions. So let us see what is next. Okay, so let me also, this is a very good remark because it helps you about your intuition. We finish after this remark. So a set is countable if its elements can be arranged in a sequence. It's an extremely useful intuition, such that every element appears exactly once. So that's extremely important. I should have written it in red, okay? So it is arrangeable in a sequence, as I defined before, but every element should appear exactly once. Thus, when you hear the term countable, you should think listable. You can list the elements. Yes?
So does every element appears exactly once mean that duplicates are removed or that they still count?
No. This means that if you can write it as a sequence, the whole set,
Yes.
in which there is no repetition, then it is granted it is countable.
Okay, so it's the set basically.
Yes.
Okay.
Yes.
Oh, the set of values, I mean.
No. You have a set. Here you don't have the notion of sequence in the beginning.
Okay, so
I just give you a set.
Yeah.
Okay? If you can count them,
yes.
say this is the first, this is the second, this is the third, and then you cover everything, then it means that you could list it in a way that every element is there for once.
I would just
So be careful, there is no sequence in the beginning.
Okay.
I give you a set. For example, I can give you this set 1, 4, 9, 16, and etc. Okay? So you can list them. Okay, so you can say that this is the first one, this is the second one, this is the third one. Okay, so that's the meaning. I can list it. Okay? Any questions? Okay, so we stop here, but I want you to think about those lessons, okay?